Hello everyone, this is Mr. Appel, and we're going to walk through graphing an exponential function using transformations. So this is the function right here that we're going to graph. Of course I know it's exponential because the variable, the x, is in the exponent we see right there. So the first thing is to identify the parent function. Now this process is a little different with exponentials in that the multiplier can be lots of different numbers. So in this case, the parent function is just y equals 4 to the x power, where that 4 could be a 2 or a 3 or a 10 or a 1.5. But recall that any number greater than 1 represents growth. And so this is going to be a growth situation, exponential growth. And so I know, and I want to predict that the graph is going to do this. It's going to be a J-curve that looks something like that, where it increases from left to right, as opposed to if it was decay, where it would do that sort of thing. Either way, keep in mind that there is a horizontal asymptote on that parent function right on the x-axis, right? Because that graph, in this case, as it goes out to the left, gets closer and closer to that x-axis without actually touching it. Okay. Now we want to identify a couple of critical points. Usually x equals 0 and x equals 1 are good ones. So when x is 0, 4 to the 0 power is 1. Anything to the 0 power is 1. And then 4 to the first power is 4. If you wanted to go one more, x equals 2, 4 to the second power is 16. That's probably going to go off this graph, so it might not be useful. And in this case, I might even want to go a negative. You don't necessarily have to do this, but sometimes grabbing an extra point can be good. But just to keep in mind what happens in the negatives. When x is negative 1, the equation is 4 to the negative first power, which is 1 over 4 to the first power, or 1/4. And so that's why as we go to the left, down here, this graph gets smaller and smaller and smaller. Okay, so there's our critical points. The next thing that we want to do is to determine the transformations. So going back to the original function here, I see two transformations. I see the x minus 3, which means this thing is going right 3 units. And I see the minus 5 after, which means the whole thing is going down 5. Now I like to apply those transformations to the critical points. I'm just going to move this down a little so I have a little room to work with and change colors. So there's two transformations taking place. There's right 3, which is affecting the x value. Now this is the one that's always a little confusing because remember that the whole x minus 3 moving things to the right 3, everything's kind of backwards. So if you think about what would shift this graph right 3 units, it would be adding 3 to each x value. So that's what we're going to do. So negative 1 plus 3 is 2, 0 plus 3 is 3, 1 plus 3 is 4, and 2 plus 3 is 5. So those are my new x values after taking the parent function x values and adding 3. Next up, we're going to go down 5. Up and down affect y values. So I'm going to take each y value and I'm going to subtract 5. So 16 minus 5 is 11. 4 minus 5 is negative 1. 1 minus 5 is negative 4. And if you want to add that fourth one in there, 1/4 minus 5 is negative 4 3/4. But that's not really as critical. The next thing is the asymptote. So our asymptote, remember, on the parent function is a horizontal. It's the line y equals 0. It's the x-axis. So if the whole graph shifts left and right doesn't affect that asymptote, right? Because if you take a horizontal line and you move it left or right, it doesn't move anywhere. But if you take that asymptote and move it up or down, it does move. And so if it was at 0 and we move the whole graph down 5, the asymptote is going to move down 5. All that is to say that the horizontal asymptote is the line y equals negative 5, and it's the up or down transformation that tells me that. I'm going to go ahead and plot that because that really is going to show us where this graph belongs. So I'm going to put that right on my graph. Now I'm going to go ahead and plot my new transformed x's and y's. The real critical points are really these two. Those are the most important. So I'm going to show you what it looks like with just those. So 3, -4 is right there. 4, -1 is right there. So that's really enough. If I know the shape, and I know this is exponential growth, I know it's doing that. That's really enough for me to graph this thing. Whoops, I missed. Let's try that again. I'm going to go from the other way. Right, so just those two critical points really is enough if you understand the shape. By adding in a couple extra points, like the 2 and -4 3/4, which is right about there, and then the 5 and 11, which should be way up there, you can see I didn't really need those aiming points. Those two critical points there were enough. And so that's my graph. That's a pretty good sketch of that graph. And the only other thing we might be asked to do is domain and range. So let's do that. So the domain, remember, is how far to the left, how far to the right. Well, this goes forever to the left, it goes forever to the right. And so our domain is -infinity to infinity. Our range is down to up. How far down does it go? How far up does it go? Well, down, the lowest it gets to is -5. It never goes below -5. And the highest it goes is forever. It goes up forever. The question is, does it actually get to -5? And remember that asymptote at y equals -5 tells us it doesn't. It gets really, really close to it, infinitely close to it, but never actually gets there. And so it's a paren as opposed to a bracket. And that is an example of graphing an exponential using transformations. That's all for now. Thanks.